Okay, let's go ahead and get started. So, hello and welcome. Again, thank you so much for joining us today. Of course, today we'll be talking about indoor 3D modeling use cases, covering photogrammetry in action. Before we get started with today's webinar, we want to take a moment just to acknowledge the difficult situations people are facing throughout the world right now. We know it's a hard time out there for everyone. We're grateful for those who are doing essential service work, and we're grateful to you for joining us today. So we're really glad to have you. So yeah, let's go ahead and dive in. So my name is Zach Dukowitz. I'm the content marketing manager here at Flyability, and I'll be your host today. And our star speakers today, we're going to hear from Lori McBean, who's a geospatial data specialist at UAS Inc., based in Sudbury, Canada. She's got a ton of experience visualizing data. And so she's going to be speaking to real use cases for indoor 3D modeling. This is something she does every day. We're really excited to hear from her and learn from her expertise. And we're also going to be hearing from Gregory Spearlett, our professional services engineer. Gregory, here at Flyability, of course. Gregory's traveled the world doing trainings on the Helios 1 and Helios 2. He has a lot of experience doing hands-on work with inspections, so we're going to be hearing from him on the drone side of things. So we're really excited to hear from both of these folks today. Really important point. We were actually talking to Lori just before we got on. Originally, she was supposed to be a keynote speaker at our user conference in March, which was going to be held in Denver, at the location of or near the location of our new US office. But unfortunately, that couldn't happen because of the pandemic. And Lori was just saying that she'd much prefer to do this in person. I think a lot of us would, right? In person means that we can ask questions, and so that's what I'm covering here on this slide. We really want you to ask questions. We want this to be as engaging as possible. Unfortunately, because we have hundreds of people on, we can't let everyone have a live microphone and just chime in. It would be chaotic. But the best thing we can do to simulate that sort of interactive experience is to have you chime in with questions. So you'll see there is a questions pane. That's what's highlighted here. You can click that caret, open it up, and type in a question at any point. You can type in questions starting now. If you came with some burning questions, you can type in questions as they come up during Lori and Gregory's talks. We'll be doing our best. We have some folks working behind the scenes answering your questions live in writing, and we'll also be curating questions for a live Q&A that we'll do at the end of the session. So please don't be shy. Please use that questions pane. If you happen to use the chat pane, that's also fine. There's a chat pane you'll see on your dashboard. Either one of those are fine places to reach out to us. So please don't be shy. We want to hear from you. And then the last thing I'll cover before I hand things over to Lori is the agenda for today. So we're going to have just a brief introduction. That's what we're doing right now. Lori will speak for 20 minutes, talking about using the Helios 2 for photogrammetry in mining. So really how to visualize the data that you collect. And then Gregory will be talking for 15 minutes about photogrammetry use cases based on his experience in the field. And then we've devoted a third of today's hour to a Q&A. So again, emphasizing the interactive, engaging component. We really want to hear from you. So please use that questions pane. We hope to hear from you. So without further ado, I'm going to hand things off to Lori. So just a quick intro for Lori. Lori, as I mentioned, is a geospatial data specialist at Unmanned Aerial Services, Inc., based in Canada. UAS Inc. is an inspection service provider specializing in underground inspections, specifically in mines. Lori is often called a magician for what she's able to do when building 3D models in unique and challenging environments. She draws from a broad background in geomatics in her work with 3D point clouds taken from mobile LiDAR and photogrammetry, making mass capture data usable, meaningful, accurate, and efficient. And she's constantly working to solve evolving technical challenges. So we're really excited to hear from her. Lori, without further ado, I'm going to pass things over to you here in just one moment. Just bear with me. And here we go.
Okay. Well, first off, I'd like to thank Flyability for letting me speak. I think that I'm very excited. I'm the biggest fan of mapping and doing photogrammetric modeling with the Elios. I got to start off with the Elios 1 and of course dealing with the cage issues and lighting, and got to participate in helping to give some feedback in terms of developing the Elios 2, and got to play with the early prototype. So I was very excited to come and present to everyone here some of our experiences. It absolutely works extremely well, but we have to be realistic about what we can achieve in some of the most challenging environments. So primarily, UAS was founded about 3 years ago by Matt McKinnon, and started off with Elios inspection drones, and that's where the business got off the ground. We now do a much broader portfolio of work in terms of 3D modeling. Hold on. Having a little trouble. There we go. So we have a couple of partners. So we have a number of the Flyability drones. We also have 3D scanners, so mobile LiDAR from Anacent, which we are also able to deploy on drones, vehicles, and other things. So we really rely on this combination to achieve all of the goals that we have and service our clients. So our clients are a wide range of mining companies all over Canada, North America, and throughout the world. We've done some projects all over. So why can we do photogrammetry with Elios 2? Well, we learned very quickly that the 4K camera that is now on the Elios 2 is really important. So having all of those pixels means we get a really good capture of the scene. The oblique lighting, so having off direction lighting is really essential to doing good mapping. Having that setback distance be able to be held at a certain distance from the objects you're mapping really, really improves the quality. And really, if we have good coverage, we can make a good model. It doesn't have to be perfect. We certainly don't often have ideal coverage. So if we have fairly good coverage, we can build a point cloud that represents the spatial model of the space that we're in. And we can do textured meshes, but really you have to commit to doing the best coverage to do a really good textured mesh for your client. So what are the challenges? Most of us have done at least some surface mapping with drones. It's fairly straightforward. At this point in the evolution of mapping with drones, surface work is pretty much automatic. Your frames all get tagged with GPS locations. Your flight planning can all be done ahead of time. You have illumination that's very nice and even because you're outdoors, and you can fix your resolution of your pixels. So all of those things lead to very consistent, very easy to generate mapping. As soon as you bring that indoors, we lose the GPS, and that means that we also lose our flight planning. So the big challenges for us at that point is, how do you build a good model? How do you build it automatically? How do you build it quickly? And what we rely on as soon as we go indoors is frame continuity. So obviously with the Elios, we do everything with video. We pull frames out of the video to create the frames that we use in our mapping. And we want those frames to overlap. So maintaining that frame continuity is the biggest challenge when you move indoors. And how we do that is we have to limit the speed that we travel, the speed that we move, as well as the speed that we change the direction that we are looking. So if you're spinning around, looking quickly from place to place, you lose that frame continuity. So anyone in here in this webinar who has taken their Elios video and or another video and tried to run it through something like Pix4D, which is what I use on a regular basis, you'll find that you might get stretches of video that work extremely well and then they break. And that's really down to your continuity between frames. And that's the challenge that we're really facing once you don't have GPS. The other aspect is you don't have any flight control. So now you're looking for your pilots to be extremely talented at understanding where they are in space and understanding what they've covered. We're facing really tight spaces. So whether you're indoors in an industrial facility or underground, you are going to be facing areas that are really hard to fly through. And maintaining good coverage of the thing that you're mapping while navigating in tight spaces is really challenging. And the other aspect is that your resolution and the geometry of the features you're capturing changes all the time when you're in tight spaces and you're looking at things from different angles. When you take that now into the underground, we have added challenges. These spaces are completely dark. You are the sun. So the drone itself is generating all of the light, and therefore you are subject to a lot of reflections, and your lighting dies off quickly with distance. So you end up with a lot of vignetting and dark areas in your frames. And that produces a lot of dark fringing and dark noise in your clouds. And that's something that we have to deal with when it comes to doing photogrammetry in the dark. We also have limited visibility and we're unfamiliar with the spaces. So for our pilots to be able to navigate and perform these flights and capture everything with proper geometry and proper overlap, it's really challenging. And that's something that comes with practice. We know that, and a lot of trial and error. The biggest challenge with doing mapping in underground spaces, in mining, is not so much the technical challenges of getting the photogrammetry to work. A lot of it comes down to the fact that these are operational spaces and we have very limited access. We're usually only given, 10 to 20 minutes in any given space. So the idea of having perfect capture of everything that you're looking at is pretty much impossible. So we also have risks like dust and water and falling rock constantly, and sometimes that dictates exactly how long we can stay in that space. And we're beyond line of sight, so we don't often have the ability to see where the drone is, so we can't navigate as easily in terms of making sure that we get our flight lines to capture everything perfectly. Couple notes on the fisheye lens. Software products like Pix4D handle fisheye lens, no problem at all. It's included in the calibration, and we can map quite effectively with the fisheye lens. It helps tremendously with being able to have a better field of view for navigating in the space. But the things that we've learned is that the changes in geometry mean that it's very difficult to use those edge features in the fisheye images to do mapping. So what that means is you have to be conscious of that and you have to fly with a lot more overlap. So just to give you a realistic view of the types of environments we fly in, this is an ORPAS that we flew into, and you can see there's a ton of water, very close quarters, and our little Ilios does quite well, very tolerant of poor conditions. And despite things like water droplets on the lens, we can still do a very effective model with this type of video. And the opposite of that is dry, dusty environments. This is another ORPAS, and you can see that there's a tremendous amount of dust being stirred up both by the drone, being knocked off of benches and shelves above it. And despite all of the noise that you see in the imagery, it's amazing we can still model with this type of imagery. So is there any technical problem with modeling underground? Absolutely not. So this is an example of perfect flight lines. You can see that despite the fact that this is all completely in the dark, the Ilios provides more than enough lighting to create a well-lit model of a 3D underground environment. Now, you have to note that this is with perfect capture. So this is 4 flight lines, so one along each of the ribs and one looking up at the corners. And we can piece that together, no problem. This model actually took 0 effort on my part. It was 4 video files brought into Pix with a couple of manual tie points only to join the flight lines together. But other than that, there is very little done to this model. This is basically click and go. And a similar example, so this is a blower stack inspection, a large space. We had very good access to this space, so we were able to fly with ideal flight lines. You can see that you can generate a very nice point cloud, and your textured mesh comes out looking very, very nice compared to the individual frame, which obviously shows the fisheye lens and the effects on the geometry of your features. But if you look at the flight lines, we had very good capture. So our pilots, like Will McKeever, are very, very talented at performing these inspections and covering the ground. And we've worked really hard at establishing what type of flight pattern works well for photogrammetry. All of this said, these are places where we have really good access and really good control. So I want to look now more at the realistic environments that we work in. One of the main things that we do in a lot of visual inspections on are bins and chutes. So they're really inaccessible. We don't have a very long time to capture them. They're narrow, and we never get an ideal flight pattern. So these will never be captured in terms of a photogrammetric flight. They're perfect visual inspections and give our clients everything they need just with the video, but we like to turn them into something a little bit more. So this is the type of environment. It's dark. All of the lighting is coming from the Ilios, and we can get in and look at the things that the client is actually asking for. They want a visual inspection of this space. They want to look at their liners. They want to look at their mechanisms. And you can see that really they can see everything that they need to see just in the video. We don't really have a need to model this type of inspection. However, we get into environments where they might be missing plates. A lot of these rock areas are self-mining. They erode and they create pockets and new spaces, and that needs to be measured. Also understanding, you know, the drawings that we have for these spaces, everything might be perfectly lined up, but once you get in there, you start to realize that plates, like on the right-hand side here, don't line up perfectly. And so that's sometimes the source of the wear and the abuse that these sites take. So despite not being a photogrammetric flight, nothing specific about how we capture these flights, just a regular inspection, we can turn them into a fairly complete point cloud and a 3D mesh. They're not perfect. They're not going to win any beauty contests, but they provide us with a lot of really useful information. So the 3D mesh allows us to understand the things that we see in the video have a context. They have a location. We can tie those features to a place. We can map these all in MindGrid coordinates, which means they can overlay them on any of their drawings. In this particular case, we were looking at the space over the chute where the liners were missing and looking at the volume that was being eroded into the rock behind. And the 3D mesh can give us a really good idea of where that might be happening. But we can also look at the point cloud and the 3D mesh in terms of actually doing measurements, creating volumes, and comparing to what we thought was the case. So we can compare that then to the drawings, to the as-built. We can model what's going on. So we can produce that 3D mesh, and it's all coordinated, and it can go into comparison with any of their other data sets. So here's another example of an area that we get called into regularly, which is to monitor erosion above the head blocks where we have wear plates. You can see that in this case, it's eroded some of the rock behind there. The feature I wanted you to note on this is that if you look at the frames at the top, those 3 frames are all captured from slightly different points of view. They're obviously not ideal for photogrammetry. So that this is, you know, if anyone has attended the photogrammetry webinar last week, we know that we want to fly in nice straight lines with good overlap. That's not our reality. In our reality, we get as much as we can in very few minutes. There's material coming down constantly. We try and fly as much as possible in a very short period of time, and then we model the best we can. And you know, you have to throw it out to something like Pix4D to be able to manage taking different frames and different geometries and pulling that all together into a really useful model. And this type of model, I would be using dimensions of those wear plates to scale the model and create something that's a metric data set that we can take measurements from and identify the volume of material that's been moved. And this is another set of bins and chutes that we looked at last week. So 2 6-minute flights. Is it complete? No. So this was not flown as a mapping project. This is an inspection to look at areas of concern. There was a very short window to get in and cover this ground. So this is what we can produce with any inspection video. So any of your Ilios videos you can run through and get a model of pretty much whatever you've covered. So if you look on the left-hand side, we've got the mesh that was created. It's not perfectly flat because there's still some noise in the point cloud, but you can see it creates a very well illuminated 3D mesh compared to the frame at the bottom, which shows what the conditions are when we're actually flying. So the photo at the bottom is an example of the type of access we sometimes have. So in the middle of that chute system, our pilot had to go through this very narrow little collar with obviously rocks suspended above the drone and a nice challenging environment to work in. And again, at the top, you can see that we capture a lot of frames with very differing geometry. We don't often have that ideal geometry, and yet we're still able to pull together a really reasonable model that gives us a lot more information than if we didn't model it at all. And another area that we get called out to very, very often are mills. We fly them regularly for inspection. They're very difficult to open to provide better access, and it takes a long time. So the in-person inspections are really only done in shutdown periods. So this allows us to get in and out in a very short window from an access port and monitor the situation between shutdowns. So we can get into the chutes and identify things like hangups and what that material is, what's holding up the flow of material through the chute system. And then we can go into the inside of the mill itself and start looking at the wear on all of the wear plates and the materials inside. Again, what I have to stress is these are not ideal situations. We do not have perfect capture. There's a lot of variation in terms of the geometry of the features that we're mapping. And we have a lot of noise, dust, and mist and other things affecting the frame capture. So if you look at the right-hand picture, you can see the effects of the reflection. So as the drone is the source of the light, when it moves over a curved surface, that reflection follows you. And that poses a lot of really big challenges in terms of photogrammetric mapping. So basically that reflection causes those rounded surfaces to disappear. So that's a challenge that we still have to deal with. There's things we can do to modify that. We can kind of turn off a lot of the front-facing lighting, which helps to cut down on that. And we can fly in slightly different geometry and try and make up for that with capturing those features sort of off the center of the frame. So from that type of flight, we can create a 3D model, and the 3D model is useful in terms of locating where in, let's say, a drawing set the features of interest might be. Certainly, it's useful to present that information. It's obviously not going to be as beautiful as the video itself. It doesn't have the same visual clarity that the video itself has. And if you notice, there's a little bit of a geometry issue at the corners of the mill. This is something that we learned through some of these flights, is that when you rely on that overlap in the outside edges of your fisheye, it's very difficult to pull that model together. So now what we do to compensate for that is we definitely fly a separate flight line along those edges to try and bridge from one plane to the next. And that's something that I recommend if you're trying to do modeling. So obviously the biggest spaces in mining are the stopes. And a lot of the original tests for the photogrammetry with the Ilios were done in stopes. It is very useful to have that visual content for geology and for operations who are trying to solve specific problems. But stopes are actually a very challenging environment for photogrammetric mapping in terms of lighting. Lighting has a limited range and it's very dusty, so it drops off very quickly. So your flight patterns, you generally don't have, you obviously don't have the ability to pre-plan your flights. You don't know the space necessarily extremely well, but also just covering the amount of space that is in these stopes. They're very large. So the time that we have available and the size of these spaces really limits what we can do in terms of mapping stopes. We use it more as a targeted tool, so we don't necessarily map an entire stope. We might do that with our laser scanner to give an overall volume, but really, in most of these situations, we're targeting specific problems. So this is an example of a face where the blast didn't go as planned. The operations guys wanted to go in and take a quick look and identify basically detonators that hadn't fired and would be of concern if they continued on in the processing. And this is a piece of what I think the flyability test flights were. You can see with an optimum flight plan, you can get a really detailed model and it looks really great. You will think that that's a black and white photo, but that is not. That is the color, and that's what makes visual mapping of things like Stopes not very interesting. They are very plain in terms of the color, but you can get a really good product out of that if you have the time to fly it properly. One of the problems we do have regularly is the dark points that we get in our clouds. So on the right-hand side, these are dark points that are correct. They are coherent with the rest of the well-lit points that we extract in our model, but they're off of areas of the image that didn't have very good lighting. So they are correct points. They are fine to have in the point cloud. They're just visually very distracting. Now the left-hand side, these are the problem points, and whenever you capture imagery with Ilios and it overlaps with the black background of looking into the distance, you'll get fringes of black points on your features. And this is really the problem that we have in terms of cleanup when we want to go ahead from extracting our point cloud and then creating a 3D model. Visually, those points basically disappear when you turn it into a mesh. So they're not really a terrible problem once you move on to that. So really the core of what we use the Ilios for most of the time are OR passes. OR passes are very narrow spaces. We have very little other options in terms of sensors that we can get into these places. They tend to block up, and the blockages cause a real problem because we're shutting down operations at that point. You're not moving material, you're not making money. The conditions inside the OR passes tend to be really rough. As you saw, we have dust, we have water, different situations, and we're always knocking down material. OR passes are operational spaces. Some of the projects we've done recently, you're waiting in between blasts to get in there, and you have a few minutes to capture as much as you can. Quite often, we have no other information available. Sometimes the OR passes are shown on a drawing as a nice straight line. That's very rarely the case. Over time, they change shape, and sometimes we don't have an accurate model of where they are. So any data that we can collect in these spaces is really valuable. We don't have a lot of other options. Ideal flight pattern is never an option in these spaces. They're much too small. And we do require accurate georeferencing to tie to the rest of our mind model, and we require accurate scale, obviously. So how do we accomplish that? We tend to do a lot of integration with our other scanners as well. So we have the nice Ilios with the small diameter. We can put it into incredibly small spaces. It's got its protective cage, so we can be really, really trusting of its ability to get in and get out. It offers a lot of visual content. So sometimes that's the main goal of these flights into the OR passes. And the limitation is that we still require a scale constraint and some referencing to put this into actual coordinates. Our other systems include the HoverMap mobile LiDAR. It flies on a really large platform, so it's sometimes very limited in terms of getting into these tight OR pass spaces. It does produce nice clean point clouds with clean edges, and it collects with an accurate scale. The problem is it doesn't offer us any visual content, so it doesn't give us a lot of feedback in terms of what's going on inside those OR passes. So this combination is very powerful. We use it quite often. As an example, we had a project, a large engineering project that we were working on. We were able to scan large sections of the area of interest, but we had areas that were very limited where we couldn't actually access. So if you look on the right-hand side, you can see we had a very small access port into an unused section, and we needed to get into there to access an OR pass that we know to be blocked. We can't put our LiDAR scanner through there, so we look at this as a combination. So the bottom shows you the point cloud that we scanned, and then we were able to send the Ilios in through that port and fly up to the area of the blockage. So the nice thing is we have the visual content. The video is there. We can take a really good look, and the engineers can take a look at what's causing the blockage, what has to be done to remedy the problem. and we also get the 3D model. So photogrammetrically, we can extract that, we can combine it with the laser scan in order to do the referencing, so it's all coordinated, and to produce the accurate scale. And now what we can do is integrate that and create a 3D mesh that's continuous mesh for all of those spaces. So that's an example of how we combine our systems to be really complementary. We get the visual content we want, we're able to get a model in places we can't access, and we still have the ability to produce an accurate spatial model as well. And this is an example just from last week. We have a critically blocked ore pass, and again, they're trying to pass material through this space, and finding that they're not seeing the throughput that they want. They understand that there's a blockage, and we have to go in and identify what's going on. So we can fly in with the ELIOS and produce the visual model. We have a partial scan with our LiDAR because we can kind of get it to the bottom of the area, but we can't get that to the location of the blockage like we can with the ELIOS. So we use the ELIOS, we have the LiDAR for scaling and to reference it, and between the two we can build a 3D mesh. And the point is, it's again, not 100% complete, but it is more information than we have from any other source, and we can't get this information in any other way. So we were able to provide them with a 3D model. They know where the blockage is. We were able to go in and measure the size of the blockage, take a good visual look at what the blockage is, and then come up with a plan to remedy that. We also do some surface infrastructure for the mines. Again, even though it's surface, we still have time and access restrictions. These spaces are very dangerous, lots of hot metal. You have very limited access locations, so you can't just go into a building and occupy the building. You have very limited points where you can go. And the scope of the project is really important to consider when you're planning these, because we don't often go in and map an entire building with the ELIOS. We have very targeted jobs that we do with it. Structural modeling is still challenging. Getting clean edges on things like metalwork is still a big challenge for photogrammetry. And often lighting is still an issue, just like it is underground. So we still have all of the same issues, and we solve it in much the same way. So as an example, we went into a building where they had a project to run some new ducting and infrastructure up through the roof. They needed a detailed model. If you look on the left, that's a very quick model from flying up and orienting ourselves in the building, but obviously it would take an awful lot of flights to produce a fully detailed model of the entire building, when really all we needed was the detailed model of the roof and rafter system on the right-hand side. But in order to map that back to the drawings that they have and understand where that is in space, we again look to integration. So in that particular case, we took our LiDAR, did a quick scan of the building, which gave us the overall shape. From that, we can then integrate the photogrammetric model in that area of interest, put it in the right coordinates. You can see from this comparison, our photogrammetric model is definitely much more detailed, right down to seeing a piece of paper that someone left tagged onto a beam when it was installed. But we have that spatial information coming from the ability to tie that back to a reference model, which came very quickly from our scanner. So why would you bother modeling your inspection? We talked about this a little bit in the webinar last week. There's not necessarily a need to model every inspection. Certainly we get called out to do visual inspections on a regular basis, and the point is the visual inspection. The operations guys want to see what's going on with their site. We don't often go into this with the intention of producing a full 3D model exclusively, but having that model gives you the context of, okay, we can see something going on in the video, but where is that in space? And that's what modeling really gives you. And the ability to compare that then to your as-builts. So we have existing drawings, we have existing data where we have the ability to overlay that data and see what's changing and what's happening and measure volumes and displacements. That's really powerful. We want to be able to make accurate measurements. So although you can look in a video and identify features, the ability to actually create a concrete measurement out of that is nice to be able to do. And overall, it gives you better communication. You can look at a video, and quite often when I watch the videos that our pilots bring back, I don't necessarily understand exactly where I am in the space, but by the time that turns into a 3D model, we can communicate much better about where features of interest lie. So here's the big point of me presenting today. I want everyone to understand that your clients and the users of this data have extremely high expectations. Everyone has watched a YouTube video or seen a model that was produced somewhere, and they want that. They want the perfect product. They want a continuous 3D model. They want it to be the full resolution and crispness of the beautiful 4K video. But they also want to be able to measure to 1/8 of an inch on any model you produce. And they will give you about 10 minutes to do that. We have very limited windows in terms of capturing things. And the biggest problem that we struggle with clients is how they consume that data. So they want it to be really, really small and compact, and they want it to be really portable. They want to be able to view it just by clicking on a link or moving it around. And the reality is we cannot achieve that. And despite the fact that I am absolutely blown away at the success of modeling with photogrammetry out of the ELIOS data, managing these expectations is really a large part of what we have to do. So part of that is understanding what your client is actually trying to achieve. So if they need data for measurements or CAD, the point clouds are an excellent source. They are noisy. They tend to be not 100% complete just due to the nature of how we capture the data. So understanding that you can still make extremely accurate measurements with your point clouds is essential, even if they don't make the most visually beautiful products. And textured meshes are fantastic. They're, as you're zoomed out, they make an excellent model to discuss, to share information. They're great for context and understanding, but they're never going to be as fine as the video itself. So you have to balance this out. And when we deal with clients, a lot of it is education. So a lot of it is, what are you trying to achieve? What can we get you? And it's not going to be the picture perfect product that you're expecting. Our captures are never going to be realistically perfect for photogrammetry because we just don't have that much time in these locations. These are operational settings. Mining is a 24/7 business, and those operations continue full time. So finding those little windows to get in and capture information is usually between loads of material being moved from one place to another. So realistically, we capture as much as possible in the windows we have. Sometimes material starts coming down through chutes and through ore passes, and we have to get out. And that's really our balancing act, is just getting as much as possible out of less than ideal capture. And lighting is never going to be perfect underground, especially when you are the only light source. So it's one thing to have artificial lighting and try and produce lighting in dark environments, but when you are the light source, you will never have that perfect, picture perfect model that you would on surface. So if anyone's seen, drone models of beautiful surface locations, you're just not going to achieve that most of the time in underground environments. And of course, most of what we're mapping is often metal, and metal is reflective, and it's very hard when you have that direct lighting to model those things. So curved surfaces and some of the reflective surfaces are still our biggest challenge in terms of producing an accurate model and a complete model. So what are the keys to success? We've worked really hard internally on planning our flights and educating all of our pilots to fly, even if you're flying for an inspection, to consider all of the things that we might want to do with that video later. So you have to plan ahead. You have to understand that you have to consider your overlap and consider the fisheye lens, and that you can't really do modeling with that outside fringe, so your overlap has to be a little bit higher. You can't turn too fast. You can't change your camera direction too much. And the biggest piece of advice is if you're flying to produce a photogrammetric model, it's a completely different project than when you fly for a visual inspection. and we encourage people to plan ahead for that. So you know, if you really need that 3D model, you're probably not looking for that 10-minute window to go in and fly. You're probably looking for a few hours in terms of covering everything successfully. So that's a quick rundown of what we do. I guess my biggest message is that absolutely, you know, there's no technical limitation to doing modeling with your Ilios. Really, the technical challenges for us are more operational. It's getting access to the site. It's the limitations on lighting and in the space that we're occupying. So the fact that we're in very tight spaces and can't fly optimal flight paths, that's really the limitation. Everything you have in Pix4D or some of the other packages, they're plenty in terms of dealing with the calibration of the lens and mapping effectively. Really, some of the key things to look at is just how you pull those frames out of that video and maintaining that continuity. So that's about it for me. I'll pass it back.
Wonderful. Thanks so much, Lori. Thank you so very much. We had lots of people chiming in, just saying how impressed they are by your work. So I know we're excited for the Q&A. We really appreciate your presentation. So everyone, we're running a little bit behind, but I want to reassure you, I know we have a lot of really amazing questions that came in. We will still be doing the Q&A. We will probably run a little over, so if you have the time, please just stay on and stay with us. But we definitely want to get those questions answered. So if you have the time, we'll probably run at least 10 to 15 minutes past the half hour. So that being said, let me introduce Greg. So as I mentioned at the beginning, Greg Spearlett is our professional services engineer at Flyability. Greg's trained lots and lots of Helios 1 and Helios 2 pilots. He's performed demonstration inspections on Flyability drones throughout the world. In addition to conducting trainings, Greg's in charge of the creation of technical documentation and training materials. So he has an intimate knowledge of the technical workings of both of our Flyability drones, the Helios 1 and the Helios 2, of course. So today he's going to be talking about inspections where 3D mapping added significant value to the data gathered. So Greg, I'm going to go ahead and hand it over to you in just one moment. Here we go. And Greg, it is all yours.
All right, thank you, Zach, and thank you, Lori, also for that presentation on mining. So it did go into a lot of depth of all the hurdles you have to overcome to create photogrammetry, and I don't think I could have explained some of those things better. So, I'm going to talk about some use cases, not necessarily mining-oriented use cases. So, as a demonstration pilot, I have the chance to fly into some pretty diverse places, not necessarily for functional inspections, but for demonstrations. But every now and then, something like really useful comes along. So this is a selection of some inspections that we, as a team of Flyability Professional Services, have done. So I intentionally chose some inspections that did not result into a huge, massive georeferenced survey grade model, but they're more of the quick and dirty kind of modelings where the end result was still a huge bonus to the asset owner. So either by providing data localization for the defects we found, or by adding an extra dimension to the defects that we found, because photogrammetry is still a form of visual inspection. It just turns a series of 2D measurements, videos, into one single three-dimensional model. So the first one will be the sewer, and this is really like a data localization kind of use case. So the idea was that we found defects in brickworks and obstructions in the sewer itself. So this is the video. That's what the video looks like. You can see a not very subtle defect on the right-hand side. But you can imagine if a single brick were missing, it would also show up on the video. The only issue is since you only know the location of the entrance of the tunnel, and assuming this is an unmapped tunnel, you can't really measure from the video exactly how deep you are inside the tunnel. So repairing this, assuming it would require digging up the streets and repairing it from the exterior, you would have a hard time finding the defect if you're just digging randomly. So this is where the 3D model really comes to shine, because in Pix4D, if you click on any point of the 3D model, you will see on the lower right-hand side, you will see a image of the frame actually that's corresponding to that particular point on the cloud. Also, you can make measurements. So by clicking between the entrance of the tunnel to the actual point where you find the defect, you can see here that it gives you a length in either meters or feet or any unit you can set up in Pix4D. So that is really where the extra information here came from. So even if you don't have extremely pretty model that has no holes and extremely high GSD, simply this feature kind of made it worthwhile to make the model. And here's a little video of, regardless of that, showing you how well the model turned out. So I'm hoping the frame rate you're seeing is doing this justice, but well, you could probably also do the inspection on the model itself, especially for the bigger holes. You can see them pretty clearly. But first and foremost, the video data will be a lot better anyways. So just to give you a few stats on this mapping project, it's basically consisted out of one recon flight and one 6-minute mapping flight. And then the images exported for making the model were all on the way in, basically. So it's just flying straight ahead. And the image I showed you, where you saw the big hole on the right hand side, that's basically the orientation of the camera as you're flying into the tunnel. And then you just export, say every 5 frames, you export an image, throw that into Pix4D, and then you can go ahead with the scale and orientation constraints. So in this case, we use the entrance diameter for scale. It's not very accurate, but it's what we had. The entire project was about 500 images, which takes about 1 hour on, this is a pretty high-end laptop. Next example I'd want to show you is the refinery we did in September, I believe, of last year. So this was an outage on a FCC unit, and basically they were looking for defects in the refractory lining. It was actually intended to be a normal visual inspection, but we still managed to use photogrammetry sort of on the spot to estimate and actually will quite accurately measure the depth of the defects. So for those of you who are not familiar with what an FCC unit is, it's basically the part of a refinery that turns heavy oil into gasoline, like lighter hydrocarbons. So basically heavier stuff like diesel goes in the bottom, and gas that you can put in your car comes out the top. This is quite an essential part for operation. These things run something like 24/7 for 5 years at extremely high temperature and flow rates. So the thing you see on the right, that's what the refractory lining looks like. It's a type of cement, heat-resistant cement, that's embedded in this hexagonal mesh structure. And this is the model we've managed to make of that. So the reason this turns out so nicely is because the hexagonal mesh structure and the texture of the cement really gives the Pix4D software a lot of texture to grab onto and to create tie points and to triangulate those into 3D model. And actually the added value of this modeling was that they could quite accurately estimate the depth of this abrasion that we're seeing in this joint between the two mesh panels. And I was on site for about 2 days. The first day we did normal visual inspection, just going up the entire pipe, which is about 50 meters high, 600 millimeters diameter. And we saw this defect, and at some point, the entire inspection department of that refinery found itself around the table looking at the video frame by frame, trying to see if this defect was a problem or not. And then the next day we went in again to exactly that point, made a quick model, and then instantly it became obvious that this was something they could leave as is for another cycle. So that's really where the value comes from, is instead of like guessing, is this a problem or not, you can really know for sure. And the way we went around making this model as a flight plan was I just basically hovered around the defect, and because it's quite a narrow tube, I had the back of the drone against the tube the whole time. I just yawed around as best as I could, and that leaves the camera at more or less the optimal resolution distance, because it's a 600 millimeter tube, 400 millimeter drone. That leaves roughly 20 millimeters, so 200 millimeters in the front. So that's more or less the focal distance of the camera. So this entire project was 370 images. It was one flight where we did the whole length of the tube, and then one more 6-minute mapping flight at the specific level. In this case, it was 28 meters above ground level. Exported the images from the video and then put it on my relatively low-end laptop. It took about 3 hours. I used the pipe diameter to scale, but to be honest, the inspectors didn't really look at the values that were measured from this model, just because these hexagonal meshes have a specific size. Their experience told them that this was not an issue, so this could be evaluated the next day. Next example is the stack. That's one my colleague did in the USA. So this started out as also a visual inspection flight. And in this case, we had the luxury, my colleague had the luxury of being able to spend a lot of time on site. So once they were done with the visual inspection, they had 2 batteries left over, so they wanted to make a model of the entire stack. And the idea of that was that instead of knowing just, okay, you have, some refractory missing approximately this long from at these locations, you would be able to measure exactly how much surface area of refractory is missing in exactly those places. So there are some issues with stacks, and some of them already were addressed by Laurie a while back. So as you look up, the advantage there is you can see these temperature probes coming, right? And that's an issue. If you fly into them, you could get impaled or damage your drone on those. So you want to keep your camera angle up as much as possible, but that's going to decay your image quite a lot, because in the close field here, you see on the top right, you can see clearly overexposure close to the drone, and then there's a sort of ring of nicely exposed texture, and then in the distance it's underexposed, and you've got then sunlight coming into the top of the stack. So that kind of tends to create a lot of false points on your cloud. So just to compromise, I think here the angle is about plus 45 degrees, so you can still see some stuff coming, and you have a very nicely lit environment as well, a very nice lit camera image. And the decision here was to do the shaft. I don't know if you can see my mouse, but I'm on the left image. You can see that there's this kind of a corkscrew green line in the stack, and that's the flight path of the drone. So it was decided to corkscrew up the chimney, and that gives you a decent coverage as you're flying up. It's definitely not as ideal as hovering one place, doing 360 degrees, hovering next place 360 degrees, or just going up and down, scanning the whole side. But it allows you to do a quick and dirty model of the whole stack in just one flight as you're corkscrewing up, because you have to fly up anyways. And then as you go to the top, as you reach the top, you would sort of slow down and fly a bit closer to the wall to get at least a high resolution image of the place where the refractory is missing. Because during the reconnaissance flight, during the initial visual inspection, it was determined that there was only refractory missing near the top. This is just a quick video to show you how the surface measurement works in Pix4D. So it's quite simple. You go into the model, and this is already in the textured mesh model. You click on the surface area measurement tool. You trace a path directly on the 3D model, and then assuming it's correctly scaled, because in this case we used the stack height as a scale constraint. It's going to give you an instant measurement in the top right corner. And this is, I think we shared this on social media a while back, but that's basically a fly-through of the entire 3D model. And you can see these dark rings. Those are actually an artifact of that flight path. As you're corkscrewing up, the stuff that's far away is not as well lit, and it's going to appear darker than the stuff that's close by. And as you reach the top, you slow down and take your time to really make a good pass on all of those places. And then later on, you can fill in the missing refractory and get quite an accurate estimate on what's missing. So some quick project stats on this as well. So this is also a really good time to mention the necessity of a recon flight, because you're tempted as you're doing photogrammetry to really, not look where you're going, because you're too interested in filming the walls of a thing. You're not seeing those, so for example, those temperature probes coming. So it's really worthwhile if you have the time to really take the time to do one flight where you're not necessarily doing photogrammetry, but just scanning for dangerous areas. And once that was done, it's 2 flights, 2 times 6 minutes to do the whole thing. Corkscrewing up just to get a quick pass on the bottom, and then spending some more time at the top. So in total, it was 1,800 images. And on my colleague's computer, which is quite a lot better than mine, it took about 2 hours processing time. And that's pretty much it. Those were the 3 use cases I wanted to show you. I also want to take this opportunity as a member of the training team to shamelessly plug our photogrammetry training course that we just finished a while back. It's a 2-day course. You will learn many tips on how to successfully model various environments. Considering the unlikely nature of someone actually being able to travel to our office to take this course anytime soon, we've also made it available online. So it's available as a kind of a webinar e-course. And I guess that's it. So Zach, back to you.
Great, thanks so very much, Greg. We really appreciate it. We're going to get to the Q&A here in just one moment. And again, we want to acknowledge we're running behind, but we do want to answer questions. So if you have the time to stay on, please do so. Quick note before we get to the Q&A, we've had folks asking whether we'll be sending out a recording. The answer is yes. Look for that recording to arrive in your inbox in the next 24 hours. And then just real quick, we want to note that this webinar is part of a series. As I mentioned at the very beginning, Lori was originally going to be presenting in person. Everyone on these webinars, we're going to be presenting in person at our user conference, but we converted all the content into this webinar series. These are all the webinars we've already done. and we have 2 more webinars upcoming. One is on drones in power generation. That's going to be in mid-May on May 14th. And then we'll be doing focus on the Helios 2, how to perform safer confined spaces inspections using drones on Wednesday, May 20th. So we'd love to have you at any of those upcoming webinars. For more information on the webinar series, check out the link that appears on the screen right now. So all that being said, let's dive into questions. I think the first question we want to start with is for Lori. Lori, regarding the accuracy of the point cloud images, how do the sizes compare to the actual asset, and how accurate are the measurements taken in the point cloud?
That really depends on how tightly you can tie it to something for scale and positioning. So sometimes, for example, the little collar, we only have a drawing. We have a drawing that says that those plates are 2 feet by whatever. So if I try and set that distance as a scale constraint in the model, I'm measuring off of something that's already worn down. So I'm trying to say it's approximately 2 feet in this location, but I know already that the feature I'm measuring has already eroded away and it's not quite at 1-to-1. So in that situation, it's going to be fairly approximate. What I have found is that, for instance, where I was combining the point cloud from the photogrammetry with the partial LiDAR scan, I was within 3 centimeters fit between the two, top to bottom. And that's really the precision of my LiDAR scanner. So it really depends on what you can tie it to. Sometimes it's a very approximate thing, as you pointed out. If all you have is the diameter of your stack or the opening, you're going to be fairly approximate. In the structural example, I could pick off beam intersections and created a whole set of control points basically for myself. So that's a little bit tighter model in that case, because I can actually integrate all of those different points and correct local distortions in terms of the photogrammetry. So if you can bring those points back into PIX, you can adjust that model directly, versus what we do with the integration sometimes after the fact, which is take a fixed model out of PIX and try and tie it to coordinates. So there's a lot of different ways of approaching it, and your accuracy is really going to change depending on how tightly you can tie it to something that's your reference.
Got it. Thanks so much, Lori. Gregory, we have a question for you from Jim, where Jim's asking if you could share the top tips for setting, scale, and referencing when you only have Helios 2 and no LiDAR to help.
Right. Yeah, so basically you use either what's there. So for example, yeah, manhole diameter. Basically the bigger the better. So if you're doing a whole stack, you're better off setting the height of the stack than the diameter of the stack. Because if you're doing the diameter, you're basically extrapolating the diameter, which means you're multiplying any error that you might have on that measurement, on that initial measurement. If you have the height of the stack, then anything, well, that's going to be the bounds of your model anyways. So any error you have will be multiplied, well, will be divided by the fraction of that initial measurement. That makes sense. So really, if you have as-built plans, for those, then I would use the biggest well thing that you have in your model. If you're making, for example, a measurement of a stope, then well, obviously you won't be able to have as-built plans of those because they wear out, etc. Like I guess you can work around that by making a model of the whole thing and then using the altimeter on the drone to get a sort of a rough estimate of how high you are at various places. But then again, that's going to be like a 10% error maybe. So like in some places where it's impossible to bring reference dimensions into, then you're stuck with guesses, I guess.
Can I add one quick thing to that? There seems to be an expectation that scale objects have to be something that you can see in a single frame, and that's not the reality. You want to find something that's as large as possible in your overall model when you're doing scale constraints. So I know when I've thrown that out to field crews and said, get me something with scale or something I can scale off of. There's definitely a perception that it has to be something you can take a frame of, but that's not really the case. You want as large an object as possible. So just exactly what Gregory was pointing out.
Awesome. Thank you both so much. Lori, we have a question. This came from a lot of people. And actually, I want to thank Quentin for asking the first question about the accuracy of point cloud images for Lori. But we have a question that's come in from a lot of different folks for you, Lori, which is, what do you use to combine Elios photogrammetry with hover map scans? And for what purpose do you use, which tool?
Two different scenarios. Like I said, when you have the ability to pull out control points out of your scan, so you pull out coordinates out of your scan and off of features, and you can bring that into Pix directly. That's really the best case scenario because you have the ability to adjust the model, and you get lots of local corrections. So you don't end up with a drift, let's say, in your photogrammetry cloud because you've constrained it really well. That's only really doable if you have features that you can recognize. So most of the time I'm in ROC, and the ROC isn't really feature rich enough for me to do that. So then I would pull it out. We use, honestly, Cloud Compare is what we use a lot of the time to bring together all of our point clouds from various sources. So that's what I would use if I was just going to produce my point cloud from photogrammetry, take that out and combine it with a point cloud in like from the LiDAR or something else. So if I have the choice, I would rather bring it in as a control in Pix4D and do a very accurate model and use as much information as I can possibly put into that model. But our backup plan, if we can't do that, is to use it just as a scale and an orientation in something like Cloud Compare.
Great, thanks so much. Another question, this is actually from our team. We're curious, have you tried other software than Pix4D Mapper with the Elios? And is the workflow similar if the answer is yes? And that's for you, Lori, I'm sorry.
Okay.
Sorry about that. It came from us, but it's for you.
Yeah, I have tried other software. Pix4D is designed from a photogrammetry point of view. So for people like myself who have a background in photogrammetry, it is a very convenient tool. I can understand how to fix problems and I can address issues very easily. So that's my own go-to. There are a lot of people who use other software. The Agisoft software is also very popular. The paradigm there is a little bit different. So if you don't come from a photogrammetry background, some people relate a little bit better with that model. The processing is a little bit different. Produce similar models. What I really find is that different software is going to perform and have strong points in different types of data sets. So occasionally there's a data set that we might fly that if you can't maintain that continuity between your frames, it's very labor intensive to pull those different blocks of video together. And so sometimes you might want to move away from a traditional photogrammetric approach and go to something more like the Agisoft or some of the other tools out there. In general, I stick to the Pix4D.
Got it, thanks. Thanks so much, Lori. And Greg, could you speak to that too? Have you tried other software than Pix4D Mapper? And can you speak to how the workflow might be different?
So for Elios 2, no, I've dabbled with some freeware. There's a free SFM, I believe, or Open SFM. Never with Elios 2 though. So I can't really speak to those workflows.
Okay, thanks so much, and thank you both. Let's do just a few more questions. I know we're running over. I think, yeah, this is a question from Valentine. She's asking, do you use manual tie points, MTPs, for building models on Pix4D? I think either of you could speak to this. Obviously, Lori, you'd be speaking from a mining perspective. Greg, you'd be speaking more generally. But Lori, let's start with you, and then go over to Greg.
Yeah, As I said in the presentation, what we count on with no GPS is that continuity between the frames. So if you get into an inspection video where you very quickly turn from one location to another, or you're traveling very quickly across space, you'll get those breaks in continuity. And that's the type of area where I would go in and add some manual tie points to connect the different blocks together and then let PIX carry on. That I have to warn you that can be really time consuming once you get those breaks in there. So you ideally want to fly with continuity in mind, because if you can, even the toughest inspection videos will just solve without any intervention. You do use manual tie points for sure to join blocks made from separate videos, and they're generally really quick. The thing I like about PIX is it's got a good environment for making those point selections really efficient, and they're also a good tool to evaluate the quality of your model. So I use that a lot to give me some feedback in terms of how well everything is matching. So I do, and it is a slippery slope. So you can fix small problems with manual tie points, but there's a real tendency if you have a very inconsistent video to start trying to tie several blocks together. And really at that point, you're better to just create separate projects for different segments of the video and use a few sparse tie points to bring it back together. Is that helpful?
That's super helpful. And Gregory, do you have anything to add about manual tie points? And is it something you've used with clients before?
Yeah, I guess my experience is pretty similar. So you'd use them to obviously need to make them to set scales and constraints, and also to merge projects. So if you have video one, you make that in one project, and video two is the next project, and you want to merge those projects into one model, you'd be using MTPs for those. As for trying to fix broken models or models that aren't converging, actually I found out that the easiest approach is just to go back to Inspector, export more frames, and see if that solves it. So since you're exporting video frames, you can basically spam Pix4D with as many pictures as you can and see if that fixes the problem.
Got it. Thank you both so much. Laurie, question for you. Because a lot of your experiences in mining, or your indoor 3D modeling experiences in mining, do you think your experiences with 3D modeling in mining could translate to other environments, like boiler inspections or other confined spaces where inspectors might want to do 3D modeling? Yeah,
absolutely. It's exactly the same issues. A lot of it comes down to the challenges with lighting. And dealing specifically once you go to industrial settings, you're going to be dealing with that reflection issue with metal, and it is a challenge. You have to get really a lot of experience with flying, I think, in terms of trying to avoid the worst case scenario in terms of those reflections. But it's exactly the same problems. The nice thing about industrial settings is you generally have access to some drawings, some engineering specs in terms of scale. So you have a lot more availability for scale constraints and things like that. So I think that's probably a little bit easier. But generally, it's the same thing. You're struggling with the same issue of positioning yourself in space and being able to see where you are. It's obviously much easier to fly a good photogrammetry flight pattern if you can see the drone. And when you can, it's not a problem to do the mapping with very good coverage and everything else. It's where you're into spaces where you can't see where the drone is, and it's up to the pilot to navigate around and provide that coverage. So that's where that challenge is. So yeah, lighting and just navigation in space, very, very similar between the two environments.
Got it. Thanks so much. I think this will be the last question that we have time for. This is, Laurie, for you from Tommy. How do you avoid having the dust that gets captured on the inspection video being processed into the point cloud model when you're using Pix4D?
Okay, so here's where I say that I'm not magic, Pix4D is magic. Drone photogrammetry is really designed around the concept of redundancy. We measure up to 50,000 key points between images. Statistically, things like dust, we're only pulling every every few frames, those dust articles move around in the frame. And so when it comes to correlation, they don't come out as being a well-fitting statistical point. And they don't seem to affect the model. We don't get dust artifact points in that model. PIX is really, really resilient in terms of that. And I have to say, even in terms of the cage, we have that question a lot is, how do you fly downwards? Because when you fly down, you do capture the cage. And I have to say, in one of the models that I showed, I have a full, perfect 3D model of the bottom of one of those chutes with a big set of chains at the bottom. And if you go through the video, I don't have a single frame that doesn't include the cage. And yet my model is complete and doesn't have any artifacts at all. And that's, again, that redundancy. If that cage is less than, let's say, 30% of your frame, and your lighting behind the cage on the surface that you're mapping is sufficient, those points just statistically don't fit well with the rest of the data. And it doesn't seem to affect what you capture in terms of your final model.
Awesome. Thanks so much. One last question. I think I just want to clarify this. We have a question from Marcus who's asking about Bentley context capture, but I don't think either of you have experience using that platform. Is that true?
I haven't used it, not in a long time. I think I did evaluate it many years ago.
Okay, so sorry, Marcus. I don't think we can answer your question just based on the experiences that we have. But I think I'm going to end things here. We've gone well over, but I think we've had some amazing information shared today. Thank you so much to both of you. Lori, I want to say we had so many people chiming in as you were sharing your models, just really stunned by your work. And obviously we've gotten to learn from you some today, and the folks that are listening in have gotten to learn from both of you. But I do want to say, if folks are watching and you've been blown away by what Lori does, this is what she does for a living. So her contact information is on the screen. If you want to hire her, there she is. So reach out. I think it wasn't the intention, but this may have been the best sales pitch in the world for your services while you were also educating us. So thanks so much.
Thanks very much.
Yeah, no, you are a magician, whether you like the title or not. Yeah, but thanks so much, Gregory. Thanks, Lori. It's been a really, really great webinar. Lots of good information shared. Thanks so much to everyone who has attended. And that'll be it for today. We really appreciate everyone taking the time to be here with us today.